Hi there, this is GCSE Physics. This is Atomic Structure Lesson 3, the history of the atom. So objectives are to establish how the model of the atom has changed over time and to appreciate that scientific understanding changes over time when new evidence is published. This one will be quite note intensive, so you will probably find yourself pausing the video and making notes, or if it's just revision, you might want to listen, maybe rewind at points, listen to points again. Let's make a start. So Democritus, he was the man that started it all. So the ancient Greeks in 500 BC, before Christ, proposed that all matter was made up of identical lumps called atomos. An atomos is a Greek word and it means indivisible, which basically meant that they believed that atoms could not be divided into anything smaller, which obviously we know now not to be the case, as atoms have things that make them up, protons and neutrons, electrons. Then you can split them up even further than that, but you learn about that when you do A-level. So let's move on to John Dalton. So it wasn't until 1804 that John Dalton brought the idea of atomos back to the attention of science. He proposed that tiny spheres, should be an S in there, called atoms were the smallest type of matter. He believed that each element, was a different type of matter. Alright, let's move on from there. So J.J. Thomson and the plum pudding model. So J.J. Thomson discovered the electron 100 years later. So Dalton wasn't entirely correct, as the atom clearly had electrons and there must be something else. He proposed that atoms were a sphere of diffuse positive charge, so it's like a spread out cloud type thing as shown in that picture, with tiny negative electrons spread throughout the atoms itself, as you can see on the right hand side. Similar to the plums in a plum pudding, hence the model was coined the plum pudding model. Then these three guys showed up. So you got Rutherford, Geiger and Marsden. So they did an experiment, which I'll go into a little bit more detail in a moment, but the experiment used something called alpha particles. These particular alpha particles are very high energy. Alpha particles, if you don't know, are a helium nucleus, and helium nucleus has 2 protons and 2 neutrons. It's the second element of the periodic table. It's got hydrogen, helium, and lithium, beryllium, and so on. Helium's the second one. So 2 protons, 2 neutrons, and alpha particles are just the nucleus. So they were fired at some gold foil, and what they expected were to pass straight through the foil, and hence the diffuse positive charge of the atoms that made up the gold foil. It's an interesting point then. The gold foil that they used in the experiment was used as it was the thinnest material that scientists could use or find at the time. The chamber that the experiment occurred in was also evacuated, which means it had air removed, and that's so the alpha particles didn't collide with the air. Alpha particles in air, it's a type of nuclear radiation, but you'll learn about it in subsequent lessons. Alpha particles in air can't actually travel very far. They might travel a couple of centimeters and then they'll stop because of all the collisions they have. So obviously it's really important for this experiment that the chamber that they conducted it in had no air inside. So this is what it looked like. So number one, you've got an alpha source. Alpha's that letter there is this one is the Greek letter alpha. It means alpha radiation. So the alpha source in a lead box. The reason it's in a lead box is so it can only get out through the gap because lead absorbs radiation. Then you've got the fixed thin metal foil. The metal was gold or gold leaf. Then number 3, you've got a detector. So it's a microscope focused on a small plate glass, and then each time an alpha particle comes through and hits the plate on the outside of the chamber, you get a spot of light that was observed by the scientists. And what they did, they moved the detectors to different positions, and at each position, the number of spots of light observed in a certain time was counted, and then obviously comparisons made depending on the angle. And finally, as we stated earlier, the apparatus was in a vacuum chamber to prevent air molecules absorbing the alpha particles. So I guess the question is, what happened? So we had the alpha source with the foil. Virtually all of the alpha particles went straight through. Most of them. A few alpha particles were deflected through small angles. And about 1 in 10,000 were deflected straight back at the alpha source. So this is very unusual. So this is what happened in the experiment. And then obviously these results meant something. For, the analysis led to a conclusion regarding the atoms itself. And just out of interest, Rutherford said that the fact that the alpha particles came straight back, he said the equivalent in terms of energy, he's firing obviously back in 1904, he's firing a 15-inch shell at a person holding a piece of tissue paper, 50 meters away, and the shell coming straight back. So in terms of energy, he said he was very shocked from what happened. Obviously, they expected them all to pass straight through. So how can the results be explained? So deflections occur because there's a force between the charged nucleus and the positively charged alpha particles. Now, scientists knew that alpha particles had a positive charge. Obviously, if the 2 protons and 2 neutrons, the 2 protons are positive. The neutrons are, of course, negative. So most of the alpha particles do not pass close enough to the nucleus to be deflected. So obviously scientists established that an atom, there's a lot of empty space if most of the stuff just passed straight through. And thirdly, backwards deflections occur when the alpha particles make near head-on collisions with the positively charged nucleus. So consolidation of the results. So the relatively small number of deflections indicates that most of an atom is indeed empty space with a very small nucleus. And the backward deflections can only occur if the nucleus is positively charged and it contains most of the atom's mass, which it does. The plum pudding model would not produce backward deflections, because the plum pudding model didn't fit that type of result. If the plum pudding model was accurate, then the alpha particles would have passed straight through. But because of all these different things that occurred, scientists then had to change the model, the accepted model. So Thomson's plum pudding model was discarded in the bin of history, and Rutherford's nuclear model became the new model. It wasn't complete because it only talks about, it got the nucleus, and but there was nothing about the neutron, and the electrons kind of weren't involved. They said that electrons would orbit, but further work was done by a guy called Chadwick and a guy called Bohr. We'll come on to them in the next lesson. Anyway, let's have a look at this. So if you want to have a go and pause this, just do this word fill. If you want the keywords, I'm going to put them on now, and then I'll take you through the answers. So according to Rutherford, an atom consists of a tiny positively charged nucleus surrounded by a cloud of negative electrons. The nucleus also contains most of the mass of an atom. This model was supported in the alpha particle scattering experiment in 1909. In this experiment, most alpha particles pass straight through a thin metal foil, with only about 1 in 10,000 being deflected backwards. And I think I said earlier 1904. That's wrong, it is 1909. Right, that's the end of that one. In the next lesson, I'll do a consolidation type starter question where we'll do like an exam style question on the experiment, and then there's a bit more information to give you on the discovery of the neutron and energy levels around atoms of the electrons. So I hope you found that useful. Thanks for watching, and I'll see you soon.